Great. Good morning, everybody. And welcome back to Calc 1. Plan for today is we're going to finish off Standard 6 with our discussion of product and quotient rules. And then we are going to jump into Standard 7, start talking about kind of the last big named derivative taking rule. We're going to be looking at the chain rule. I've got my usual office hours today at 11 and at 2. Tomorrow at 10 and at 1. And as far as homework goes, I posted a new web work assignment that will be due on Monday. And we will also be having a Standard 6 quiz on Friday. I have a big pile of quizzes to pass back, so we'll go ahead and do that. Hannah. Paul. Tyra. Aiden. Riley. Joseph. Will. Emily. Cecilia. Rachel. Bennett. Mackenzie. Pietro. Laura. Helen. Vera. Vic. Wynn. John. Ryan. I don't know why I always put this column for you. I'm not sure. Logan. Damn. And gadzooks. Someone turned in a standard 5 quiz without putting their name on it. If that is you, let me know after class and I can give it back to you. Okay. What do circles and beaches have in common? What circles and beaches have in common is that they both have tangents. Okay, so when we left off last class, we talked about the product and quotient rules for how do you take derivatives of expressions that you get when you multiply two functions together or divide one function by the other. And we said that unlike with the sum and difference rules, which basically work the way you would hope they would, the derivative of the sum is the sum of the derivatives, did it with differences. Products and quotients aren't so nice. You can't differentiate f times g by just taking f prime times g prime. Instead, what we saw is that we needed to take f times g prime of x by taking the first original function f of x times the derivative of the second, g prime, plus f prime times g, the derivative of the first times the original second. And for the quotient rule, he said that if you're taking a function f of x divided by g of x, and you want to take the derivative of that, you got to do some low, 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 high, high, low. Merely, low square down below action. So, what I'd like to start with today is I'm going to look, it's going to be on the, let's see, 1, 2, 3, 4th page of the packet. I'm going to look at the function f of x equals 3 divided by x to the 4th. Here's my challenge. I think we have 2 different techniques that we can now use in order to help us differentiate this. What would y'all like? Rachel, what would you like to try first? Okay, so when you say, what do you mean by when you say use the exponent rule?
Like the derivative of the x to the 4th is 4x.
Okay, so this thing is going to have a derivative of 4x cubed. And the derivative of our numerator. Okay, and you propose that we use the quotient rule in order to help us differentiate this? Let's give it a go. Okay? So if we use the quotient rule in order to help us find the derivative, we're going to need to do some low d high. Derivative of high is 0 minus high d low. Merrily. X to the 4th squared down below. And we end up with this expression using the derivatives that Rachel found. Is there any way in which we could simplify this?
You can distribute the -3 into the 4x cubed.
Okay. And then this term, who cares, being multiplied by 0. All right, so that'll give us a -12x cubed.
The x to the 8th on the bottom.
Aha, we can, since we're taking x to the 4th squared, that's the same as x to the 4th times x to the 4th, which is going to give us an x to the 8th. And then I think there's one more thing we can kind of do here to help us simplify. Is this it?
You could do -12 over x to the 5th.
Cancel out the 3 factors of x in the numerator with 3 of the factors of x in the denominator, and end up with -12 divided by x to the 5th. So it's a good nice application of using the quotient rule to help us differentiate this expression, where this x to the 4th term just ended up getting multiplied by 0 in our low d high, so it didn't end up mattering. However, I claim we didn't need to use the quotient rule to differentiate this. Zach, I see you nodding your head. Can you think of another way that we could differentiate f of x without having to rely on the quotient rule at all?
The power rule.
Ooh, okay. How are we going to do that?
So you're just going to move the x to the -4, so it's not on the bottom, and then you just use the power rule.
Okay. So you want to rewrite our original function. Instead of writing it as 3 over x to the 4th, how would you rewrite it?
3 times x to the -4th.
3 times x to the -4. Cool. And then what would we get if we end up differentiating that using the power rule?
Same answer. Or just -12 to the x to the -5th.
Ooh. Well, if we pull down this -4, we get a -12 x to the -4 minus 1, which is indeed Negative 12 divided by x to the 5th. Awesome, awesome. So the moral of the story is, sometimes depending on the function that you're looking at, you might have multiple ways to help you differentiate it. Rachel preferred to kind of use the quotient rule, which got us to negative 12 over x to the 5th. Zach had the idea of, let's just rewrite this as a negative exponent and then use the power rule. And in general, you can use whatever derivative techniques you want, as long as you use them correctly. Sometimes, not always, but sometimes you will get a choice of derivative taking techniques like this, where sometimes doing something a little bit sneaky can save you a bit of work in the end. Any questions, comments, or concerns? Okay, in that case, in the bottom of this page and on the next page, there's 4 more problems involving taking derivatives of stuff involving some products and quotients. So what I would like for you all to do is to take a couple minutes and see what you can make of these next 4 problems. And as always, you're welcome to work with your neighbors or to flag me down and ask any questions you might have. And then we'll come back together here in a couple minutes and take a look at what you found. If you finish these 4 problems, I encourage you to turn to one of your neighbors and see if they agree with you. needed, huh? If you feel confident in your answer to these 4 questions, go ahead and take a look at the back page, see what you can make of that. Alrighty, let's come back together now, and I'd like to talk about 2 of these in particular. So first of all, let's look at this first one. F of x equals 3 plus square root of x times 2 plus square root of x. And I'm curious to hear what your all strategy was in approaching this problem. Anybody care to share what they did for how to differentiate this function? Yeah.
I multiplied it out first, and then went with the x, like the power rule.
Okay. So you went ahead and FOILed out this expression and then just differentiated what you got after you FOILed?
Yeah.
Cool. Would you mind sharing what you did when you multiplied out f of x?
I got 6 plus 5x to the 1/2 plus x.
Okay. So the 6 comes from 3 times 2. The plus 5x to the 1/2 comes from taking 2 radical x plus 3 radical x to get 5 radical x, or 5x to the 1/2. On a side note, sometimes it's fun to just call the square root of x radical x. Sounds snappier. And then square root of x times square root of x will give us an x. Okay, cool. So Sam, when you use the power rule to help you differentiate that, what did you find?
Got 5/2 x to the negative 1/2 plus 1.
Sounds good.
And then I made that 5 over 2 radical x plus 1.
5 over 2 radical x plus 1. Using the fact that x to the 1/2 is radical x, and the negative 1/2 means you put it in the denominator. Any questions, comments, concerns? Anybody have a different approach to working on this one? Fair?
I use the product rule where you multiply the derivative of 3 plus the square root of x times 2 plus square root of x, and add that to the derivative of 2 plus square root of x times 3 plus square root of x.
Okay, so you went ahead and actually treated this as a standard 6 question, unlike Sam who treated it as a standard 5 question, and used the product rule to help you differentiate this out. Sounds good to me. Product rule does not start with an R. Dr. Gerstle knows the English language. So, Vera, what did you get? So, if we do that, we'll get 3 plus square root of x. And what did you get when you multiplied that by the derivative of 2 plus square root of x?
I got 3 halves x to the negative 1/2 plus 1/2.
Okay, you already multiplied that out.
Oh, you're asking for the derivative?
Sorry, I probably phrased that question poorly. But yes, what did you get when you differentiated 2 plus radical x?
1/2 x to the negative 1/2.
1/2 x to the negative 1/2. Sounds good. And then we'll multiply that out here in just a second. Plus the derivative of the first function times the second. What did you get for the derivative of the first function?
1/2 x to the negative 1/2.
Gadzooks, it's the same as the derivative of the other one, because this constant terms 2 and 3 don't actually affect the derivative at all. Times 2 plus square root of x. Okay, Vera, what did you get when you, what did you get when you multiplied out these first 2 terms?
3 halves x to the negative 1/2 plus 1/2.
Plus, square root of x times x to the negative 1/2 is the same as x to the 1/2 times x to the negative 1/2. So in multiplying this term by this term, the x parts cancel out, and we're just left with a half. And then, Vera, how about these 2 terms?
X to the negative 1/2 plus 1/2.
X to the negative 1/2 plus a 1/2 again. And then I think we can combine these to get, let's see, I'm going to write this as 2 halves x to the negative 1/2. Just so we can add the fractions, we'll get 5 halves x to the negative 1/2 plus a half, which is going to come out to a plus 1. And I think is going to give us the same answer in the end as what's. Yeah, nice job. So just like before, this is an example of a problem where we couldn't use the product rule to help us differentiate this, or we could multiply it out first and then differentiate, kind of save us a step or 2 along the way. I think this way was a little bit less messy, but this way definitely got us to where we needed to go in the end as well. So how about h of t equals t cubed plus 1 over t cubed plus 1? Okay, Zach, I know what you're going to say.
It's going to be 0.
It's going to be 0.
The h prime.
How do you know that?
Because this is essentially just x over x. It's going to be 1. It'll be a constant.
X over x. How about t over t?
Yeah. And so that's going to be a constant. Like if you were to graph it, it's going to be 1. There's going to be no instantaneous rate of change. So this is going to be 0. It's going to be 1 across the board.
Yeah, so Zach had a very sneaky approach to this one. He noticed that the function I gave you was actually just a constant function, h of t equals 1 in disguise. Except that t equals negative 1 where it's undefined. So right away, I think what Zach said is, we have a constant function, a flat line. What's going to be the derivative of a flat line? The slope at every point? It's going to always come out to 0. Alternatively, you could have used the quotient rule to help you differentiate this. And if you did that, you would say you would get something like t cubed plus 1 times 3t squared minus t cubed plus 1 times 3t squared all over t cubed plus 1 quantity squared. And then these two expressions are the exact same, so they'll cancel out to give us a 0 in the numerator. And 0 divided by t cubed plus 1 quantity squared is still just going to be 0. So whether or not you see that the function is a constant function to begin with doesn't actually change the fact that once you differentiate, your answer should just come out to 0. Through brute force quotient rule or through trickery. Any questions or comments about either of these problems, or the two we didn't talk about? Alrighty, so let's see. Let's take a look at this problem on the back page here, where, as I promised, we're going to be car salesmen. So in this problem, we're going to look at two separate functions. The idea is that we're selling Toyotas. And we know that T days after the new Toyota comes onto the market, we know how many cars we can actually sell that day. Specifically, Q of T is going to be 6t minus 2t squared. Cars sold after T days. On the other hand, we also know something about the profit that can be made per car sold. Specifically, that for each car sold, T days after it comes on the market, we as the dealer can make a profit of P of T equals 10,000 minus 100 T dollars per car. So now we have these two separate functions that we're looking at. The number of cars we can sell after T days and the amount of profit we get for each individual car that's sold after T days. P of T is probably going to be something that goes down as T gets bigger, corresponding to the fact that the further it is, the more days pass after the launch of the new car, the less excited people are going to be to buy it. And so they're going to want to pay lower and lower prices as time goes on. So here's my question. How can we tell what the dealership's total profit is going to be T days after the model comes on the market? No, say T days after. So if we wanted to come up with a formula for what's the total profit going to be from selling these Toyotas after T days, what can we do? Rachel?
Would you multiply Q of T and P of T?
Multiply them? Why would you do that?
Because Q of T gives you how many cars sold, and then you multiply that by the profit per car.
So you claim that if we take the profit per individual car and then multiply by how many cars you sell, that's just going to give you profit as a whole? Does that sound reasonable to you? Yep. I would agree. Let's see. Let's use TP of T for total profit, not for toilet paper. And And we can say that our total profit, T days after, after the introduction, is in fact going to be Q of T times our P of T for number of cars sold times profit per car, which is going to give us 6T minus 2T squared times 10,000 minus 100T. What's our units going to be here? Looking at total profit after T days, what are we going to measure our profit in? Dollars, days, dollars per day, cars per dollar, days per car, meters per second. Again,
Multiply the units of Q of T and P of T together, it would be dollars per car times the number of cars, so it would just end up being dollars.
yeah, I think that's a good way to think about it. If we take our units for Q of T, Q of T's units is just going to be cars. And if we take the units for P of T is dollars per car. And if we want to find the units for total profit, which is Q of T times P of T, that's going to give us our total profit units. And if we multiply cars by dollars per car, the sort of cars in the numerator and denominator are going to cancel out, and we're just going to be left with dollars as our final unit here. So if you're ever unsure about what units you're going to get when you have like multiplying or dividing two different expressions, this is always a good way you can think about it, is that if total profit is equal to the product of Q of T and P of T, then the units for total profit should be whatever the units are for Q of T multiplied by whatever the units are for P of T. In this case, as Mackenzie pointed out, if Q of T is measured in cars and P of T is measured in dollars per car, we can sort of combine those to get cars times dollars per car, and then the cars in the numerator and denominator will cancel out to just give us dollars. And if we had done something like Q of T divided by P of T, then our units would have been units for Q of T divided by units for P of T. So our total profit is going to be measured in dollars, which hopefully makes sense. You want to say what your profit is. Profit's probably going to be measured in some unit of money, which comes out to 6T minus 2T squared times 10,000 minus 100T dollars. So now my follow-up question is going to be, at what rate is the total profit changing at T equals 5 days? So let's say we're the manager of this Toyota dealership. I know, hefty line of work, but you all are responsible adults. We're close to it. You're Hillsdale students, so you can do it. We want to know how much is our total profit going to be changing over time? Meaning, are our profits going to expected to go up each day, or are they going to go down from day to day? And so we might be interested at 5 days after this new Toyota comes onto the market, looking at and actually determining at what rate is this profit changing over time. So what do you think we need to find if we're going to be looking at the rate at which total profit is changing? Oh,
You'd want to find the derivative of total profit.
okay. And at what value of t?
Well, first you would just find the derivative and then you would plug in that, and then you would plug in 5.
Okay, so you want to find a general formula for Tp prime of t, that's a mouthful, and then plug in t, little t equals 5 into that formula? Sounds good. Okay. And I'll let you propose how we go about finding the derivative of total profit.
I would multiply out the 6t minus 2t squared and times 1000 minus 100t.
Okay, so you're proposing we FOIL this expression out first and then use the derivative? Does that sound reasonable to everyone? Yes, Dr. Gersel. Thank you. So I think that's certainly something we could do. The other approach would be to use the product rule to differentiate as is. So we rewrite out our just Tp of t. Let's see, what are we going to get? Our first two terms are going to give us 60,000 t. Our inside terms are going to give us a minus 20,000 t squared. These are big numbers. That's what happens when you deal in cars. Outside terms are going to give us a minus 600 t squared. And the last two terms are going to give us a what? Plus 200 t cubed. And I think we can combine these to get 60,000 minus what? 20,600 t squared plus 200 t cubed. If we combine the minus 20,000 and the minus 600. So Helen, what are we going to get now if we differentiate this expression?
So you'd get the 60,000 would just become 0. Then you take out the 2, so it would be 2 times the negative 20,600 t. And then you get 3 times the 200 to the t squared.
Which is going to come out to
600 t.
indeed. Yep. So here, don't let the big scary numbers scare you too much. We can just use the power rule the same way that we've been doing it. As Helen pointed out, the derivative of 60,000 is just going to be 0, since constant expressions always have a derivative of 0. Art?
Was there supposed to be a T attached to 60,000?
Yeah.
A T attached. Oh my gosh, we lost a T.
Yes.
How'd that happen? I clearly blame Helen for this and not myself. Okay, so I don't think, so this is not a constant function, so its derivative is not going to be 0. We're going to get 60,000. And now, Ellen, what's our last step going to be?
You would plug in 5 for t everywhere.
Yeah, so we're going to end up having to plug in 5 for little t, since the question's asking at what rate is the total profit changing at 5 days. And that's going to give us 60,000 minus 41,200 times 5 plus 600 times 25, which Dr. Gerstel's going to use his magic professor powers to tell him that this comes out to negative 131,000. No, I didn't actually do that in my head. I had it worked out ahead of time. Negative 131,000 watts.
would be
One more, Helen? Okay, dollars? When do you agree with that?
No, because it's the derivative, so, change in dollars. So.
Yeah, somehow need to account for some sort of change in dollars. Sam? What do you think?
Just a stab, I'm gonna say like dollars per day.
Dollars per day?
Yeah.
Interesting. What's your reasoning?
There's days up there, and there's also dollars. You gotta put them together.
This is true. Dollars and days are words that are written on the board. Riley, what were your thoughts?
Well, I also thought it was dollars per day, because the two functions that we were using, the Q and T, Q was in days, the P was in dollars. And I know we could probably, like, have a better explanation like we did for the other one, but yeah, T is in days, and we're looking for dollars. I don't know, sorry, that's a bad explanation.
That's okay. I like it better than Sam's explanation if it makes you feel better. Go ahead, Sam. Rachel, you had your hand up.
Oh no, it's just.
Oh, you're doing the resting. I like dollars per day. I think that's going to be what's it. And the reasoning is, just like when we were looking at our old velocity problems of f of t is measured in miles from home, what does f prime of t represent, or change in f of t represent? We said it was miles, the units of the original function, divided by units of time, so like miles per hour or miles per minute. Same thing's going on here, where the original function, tp of t, the total profit function, as we determined, as let's see, I think as McKinsey determined, was measured in dollars. So tp of t is measured in dollars. So when we differentiate, if we're measuring how is that total profit changing over time, when we think about it as changing over time, we want to have the original units, dollars, divided by our time units in the problem, which is days. So I think we're going to end up with negative $131,000 per day. Meaning, at the time t equals 5, if our total profit was changing at a constant rate, each day we'd be making $131,000 less than the previous day. Which at some point would cause our total profit function to become negative, and at that point in time, we probably should stop selling this car because we're just losing money on it after a certain point. The demand's not there anymore. People aren't willing to pay as much as it costs to manufacture it, say. Any questions or comments? So, moral of the story is, when you're taking derivatives like this, sometimes you have to think about these sorts of word problems where you might have to think about how is the relationship between these individual pieces going to influence something like total profit. In this case, cars sold times dollars per car sold is going to give us our total profit in dollars. And then differentiating maybe can be done in multiple ways. Helen proposed to multiply out our TP of t and then differentiate. In my notes, I'd actually use the product rule on this function to differentiate, and then plug in t equals 5. But however you do it, you should be able to come up with a valid answer in the end. And don't forget to keep track of your units. Questions? Comments? All right, in that case, it is time for the next standard, and for a bit of a history lesson, the eternal battle between Newton and Leibniz.
Thank you.
So before we jump into our next derivative rule, I want to talk a little bit about the history of calculus, which is something we haven't really done yet. And this is Hillsdale. We're a school that cares about history, so probably a good idea to kind of talk about this. As a bit of an aside, before this idea of instantaneous rate of change being measured using units and having formulas like power rule and product rule and quotient rule to help us differentiate expressions, the idea of how would you measure instantaneous rate of change was actually measured by something called infinitesimals, which I'll write that out on the board. Anybody see any words buried in infinitesimals? What?
Infinite?
Infinite? Then smalls. Leave off that S at the end. Infinite small is basically the word, corresponding to the fact that infinitesimals, you could think about, were real numbers that were infinitely small, that were smaller somehow than other real numbers. So in other words, numbers that are close to zero, but aren't actually equal to zero, but they're so much closer to zero than any number that you're used to working with. And the idea of doing math with this sort of idea of infinitesimals to measure instantaneous rate of change was, it was weird. And I'm not going to go into great detail about how they were used because we certainly aren't going to really be using them in this sense. But when you think of infinitesimals, think about numbers that are infinitely small. And then the idea of limits came along as a way of avoiding these infinitely small numbers, and that led to kind of modern calculus. But there are two guys a few hundred years ago who came up with the idea of our more modern day calculus at basically the same time. One was Sir Isaac Newton, and the other was Gottfried Leibniz. And it's kind of a famous classical math story in that they both came up with ideas for calculus pretty much simultaneously, and then they fought with each other for the rest of their lives as to who came up with it first. They both wanted to take credit. And to this day, mathematicians still argue about, no, calculus is Newton's invention, and Leibniz somehow saw some of Newton's work and sort of stole it, or no, Newton saw Leibniz's work and stole it. No, they came up with it independently at the same time.
What do you think?
Say what?
What do you think?
What do I think? I think I wasn't around back then, so I can't really say. So, also, I'm not tenured yet. I don't want to get into the middle of these big mathematical fights. So, the reason why I'm bringing this up is I want to talk a little bit about the different notation that each of them used for what it means to take a derivative of a function f of x. Because they have different notation, and the two different forms of notation are going to give us a couple different ways to look at our next big derivative rule.
is Lagrange?
Lagrange, French mathematician who isn't really getting credit for coming up with calculus, but he basically took Newton's notation and tweaked it a little bit to be the notation we're now used to. Yeah. I don't know. I threw him in the packet as a bit of a, because I don't know. I don't want to plagiarize in this class. Plagiarizing's bad, don't do it. So I should probably include his name as coming up with a more modern way of writing out Newton's notation. But Newton's notation for writing out the derivative of a function f of x is the one we're used to, the f prime of x. Newton himself originally wrote it as something like this. F of x with like a dot above the f. But Lagrange, who came around a few decades later, is like, that's weird. I like this better. So now we kind of use, in calculus, we use Lagrange's, Newton/Lagrange's notation for writing out the derivative, and we get f prime of x. And the spell. Leibniz's notation, though, was a little bit different. Instead of writing out this f prime of x notation that we're used to, he had a different sort of notation for the derivative of f with respect to x. He used the language df dx. Or if you prefer, d dx of the function f of x. And both of these are different ways of saying the same thing that Newton was saying, just different notations of saying take the derivative of a function f with respect to the variable x. ddx, I want you to think of as being something called if you're a fancy real analysis student, I would say it's a differential operator. But for you all, when you see this ddx, don't think of that so much as being a fraction. Think of it instead as being like an expression that says take the derivative of whatever comes next. So for instance, if we were to say take ddx of 3x squared plus 1, that means take the derivative with respect to x of 3x squared plus 1, and that'll give us 6x. So, might be thinking, Dr. Arstel, which of these notations do you want us to use? And my answer is going to be either/both. Because for the rest of the semester, there's going to be some circumstances under which I'm going to prefer to use Newton's notation. And there's also going to be some circumstances under which we're going to be using Leibniz's notation going forward. Because sometimes one's a little bit easier to work with than others. So I'm going to talk briefly about one advantage to each of the different types of notation, just to kind of motivate why are we doing this. So first of all, can anybody think of a scenario of a reason why you might prefer to use Newton's notation as opposed to Leibniz's notation for taking the derivative of f of x?
It's just simpler, it looks cleaner.
It's simpler, it looks cleaner, just having this f and an apostrophe as opposed to having to write out df dx. Cecilia?
It might be easier to like plug in for x, like in the equation with the cars we did when we were plugging in like a number of 5. It's easier to write f prime of 5 than like.
than trying to say
Yeah.
something like ddx of f of x at x equals 5. You could just say it's f prime of 5.
Mhm.
Yeah, I would agree with both of these. It's a little bit simpler to write out and easier to write out an expression when you want to plug in a specific number for, say, x. And plugging in a specific number for x. So for instance, if we have our f of x equals 3x squared plus 1, and we want to take the derivative at x equals 5, we could say, well, first of all, f prime of x is 6x, and f prime of 5 is then 30. We don't have to try and worry about writing out something like df dx at x equals 5. That's how you would write that out using Leibniz's notation. Is equal to the expression 6x at x equals 5, which comes out to 30. I think I would agree with you, Cecilia, that I find Newton's notation in this regard a little bit nicer, a little bit simpler. We don't have to have this weird looking vertical bar to say, take the derivative and then plug in x equals 5. You can just say, take f prime 5. I also agree with you, Helen, that it's just simpler in general, looks a little bit nicer to work with. So on the flip side, anybody think of any reasons and any circumstances under which Leibniz's notation might be easier or nicer to work with? Laura?
It might be more obviously the derivative, like the little f prime mark might be harder to see.
If you write out something like d dx, that's certainly, you're not going to miss that. Whereas if I were to write something like, might be easy to miss that. There's an apostrophe there. You're supposed to be taking a derivative. Yeah, it's certainly no bones about it. There's not, unless I were to do something really cheeky like this, you're probably not going to miss the d dx as easily as you would miss the f prime. Any other reasons? Well,
maybe if we were like changing the y values somehow, or like the f of x, because can't you also do dy dx for certain things? So maybe like in those situations for certain rates and stuff, it could be helpful.
Riley's already thinking ahead to standard 8, where we're going to be doing implicit differentiation, and we'll have multiple variables we could potentially be differentiating with respect to in our problems. So yeah, I would agree with that. So one reason, and we haven't really encountered this reason yet, but we're going to later on, for why we might prefer to use Leibniz notation for taking the derivative, is it's easier to work with multiple variables. So for instance, if we have an expression like f equals 3x squared plus 3t squared, and I told you, let's differentiate this with respect to x. Writing out f prime is equal to 6x plus 0, maybe. But what if I also wanted to know, what if we're treating x as a constant and t as our variable, and we wanted to differentiate with respect to the variable t instead? You probably don't want to use f prime for both of those, because it's not nice to use the same language, f prime, for two separate things, for the derivative with respect to x or the derivative with respect to t. So using Leibniz's notation, we could say something like df dx is going to be 6x, whereas df dt is going to be, say, 6t for this particular function. And we're going to see a lot of this going forward, functions that have multiple variables in them, and we want a nicer way of keeping track of which variable is where we're taking our derivative with respect to. There's one more scenario in which I think Leibniz's notation is a little bit nicer to work with than Newton's notation, and that's if we don't have a name for our function. So let's say we had the expression 5x cubed minus 8. And I wanted you to take the derivative of this. If we were to use Newton's notation for writing out what's the derivative of this, we would need to have a name for this expression, like an f of x, a g of x, an h of x, a smiley face of x, if you prefer. But with Leibniz's notation, we don't need to give this function a name. We can just say, hey, take the derivative of this with respect to x, and it comes out to 15x squared. No need to give it a name unless we really want it to have a name for whatever reason. So Leibniz's notation is nicer to work with if we just have some expression that doesn't necessarily have a name, but something we want to differentiate. We can just say, do the old d dx of that expression to tell us if we're differentiating. Whereas with Newton, we would have to give it a name first. All right, that's going to do it for today. We didn't really get to any of the homework 9 stuff because we ended up spending more time talking about history than I had anticipated. So I'm going to push homework 9 back to be due next Wednesday. And then on Friday, we'll talk about the stuff, what you need to know to be able to do that homework 9.
We have our exam next week.
I'm going to talk about that on Friday.
Bye.
Because I'm not sure, it's either going to be next Friday or the following Monday. I have to look at my schedule to determine exactly when I will. I'll announce that on Friday.
I know.
Oh, yeah, Zeus.
Yeah.
Yeah, let's see.
I literally cannot keep my eyes.
You want to come by to talk about stuff or do a recess? How about, could you do noon today? Okay, how about let's plan on that day?
Okay, thank you.
For 11:50, or if you could get out of class or whenever. I'll be around for a little while after this.
I think this one's mine.
Oh, it's yours?
Spaced out.
Yeah, it's Zeus.
Yeah.
Okay. Yeah, I'll go ahead and add that to my grade book then, and there you go.
You.
It is.
No problem. Have a good one.
Thank you, Dr. Bristol.
Take care.